So now we're going to be dealing with examples of metric spaces. So we actually want to prove that, okay, any metric given is actually a metric. And what are you going to do? You're going to show that it satisfies 4 axioms that we've known in the first video. So for this, right, so how do we prove this? So remember, we're going to have, so our metric here is D. So we have Cartesian product. Remember, x and y are in reals, so we have to have Cartesian product of reals. Cartesian products means you have x from real, you have y from real. So you have the Cartesian product of reals goes to some real positive. Okay, so we can say maybe D, which is a subset of real, right? Real positive subset of real, where this is actually, remember, your distance can be 0, then it's less than infinity. So this is defined as this, the usual metric, right? So we have this as the usual metric in R. All right, so we said we have to prove for the 4. So the first one says 0 is less or equal to dxy, which is less than infinity, right? So now remember that your x and y are in real. So x and y are in real. You have to work with this, right? With this definition, x minus y. This is what you want to show. 0 less or equal to the absolute value of x minus y less than, this is what you want to show, right? So you have x and y for all x, y in real. Definitely, if you have 2 real numbers, right? If you subtract 2 real numbers, it will also be in real, right? And also, if you find the absolute value of these real numbers, right? And you know the absolute value will be positive, right? If you subtract 2 numbers, whether positive or negative, if you find the absolute value, you have positive, right? So then you have 0 less or equal to x minus y less than infinity. So remember, this is our range, right? This is the range. That is the output. This means infinity is not included in this set. So so this will actually be this. So remember, this is less than infinity. So this will be less than infinity. Then 0 is less or equal to this. Remember, this is what? This is non-negative. So now the second one is to show when is it equal to 0. Definitely we know that it is greater than 0, but when is it equal to 0? That takes us to axiom 2. Axiom 2 says that it will be equal to 0, right? Dxy equals 0 if and only if x equals y. If, so the first part, if dxy equals 0, what does this mean? X minus y equals 0. When will the absolute value of a function or a value or an expression be equal to 0? That is actually when the expression is equal to 0. X minus y equals 0. So that is the only way we can have absolute value of an expression equal to 0. And from here we have what? X equals y. So that is the if part. Now the only if, right, which is the other way, when we have x equals y, if we have x equals y, then we have x minus y, right? Now substitute x equals y here, so you have x minus x, and this is dxy. So dxy equals 0, right? So we've shown that this is what is equal to 0 if and only if x equals y. Then we move to the third one. The third one says the xy is actually equal to dyx. That is the distance. This is not necessary to be d. It can be rho, it can be mu. It's just a metric. So it's saying the distance from x to y is actually equal to the distance from y to x. So remember, the xy is actually equal to absolute value of this, which you can write this way, right? This is same thing when you multiply through by negative, you have x minus y. And remember, when you have negative in absolute value, it makes it to be what? Positive. So you have this. And if you check, now instead of x, you have y here. Instead of y, you have x here. So this actually implies the xy. So this implies the xy is actually equal to dyx. So the axiom is settled. Then for M4, so we have what? Now we have, when we have z in real, then the distance from x to y is actually less or equal to distance from x to z, then from z to y. So how do we have that? So we have x minus y, that is our dxy. This is actually equal to x minus z plus z minus y, right? So we have this. Then this is less or equal to x minus z plus z minus y. So if you don't understand this, if you've not used it before, you can actually ask in the comment section, and I will do a separate video tagging this video to explain how you can have this. So it's also triangle inequality. So you can separate it this way, which is, remember, this is definition for distance from x to z, and this is definition from distance from z to y. So all the four axioms have been satisfied. So this implies that D is actually a metric space, where D is the usual metric. So let's solve probably one or two more examples on metric before we move forward. So check the next video for another example.